All right, let's talk about the secret language that powers, well, pretty much all of modern AI. And no, it's not Python, it's not C++. It's a hidden world of numbers that represent the meaning of words. This is the absolute foundation of how models like ChatGPT actually understand us. And today, we're going to pull back the curtain and see how it works.
So let's start with a really simple question. How does a computer know the difference between Apple, the fruit you eat, and Apple, the company that makes your phone? For you and me, it's obvious, right? It's all about context. But a computer doesn't see words, it only sees numbers. So the real puzzle is, how do we translate our rich, messy, beautiful language into cold, hard math that an AI can actually work with?
Okay, so the very first step in this whole journey is turning words into something called vectors. Now, don't let the name scare you. A vector is just a list of numbers. Think of it like a coordinate on a map. We have to give every single word its own unique mathematical address.
But before we can do anything else, we've got to break our text down into manageable chunks. This is called tokenization. You take a sentence, say a cute teddy bear, and you just chop it up into pieces, or tokens. It's the first absolutely essential step for any language model out there.
So now that we have our tokens, how do we turn them into those number vectors we talked about? Well, the first idea people had was something called one-hot encoding. Imagine you have a giant dictionary of every word you know. For the word soft, you create a vector that's all zeros except for a single one in the spot for soft. Same for a teddy bear, it gets a one in its own unique spot. Simple, right? Kind of logical. But this simple idea has some massive problems.
And this is where that simple idea just completely breaks down. First off, the vector sizes are insane. If your vocabulary has 50,000 words, every single vector is 50,000 numbers long, and almost all of them are zeros. Super inefficient. But the real deal breaker is this. There's absolutely no sense of meaning. Mathematically, the vector for soft is just as different from teddy bear as it is from airplane. The model has no clue that some words are related. It's a total dead end.
Okay, so one-hot encoding was a bust. But then, back in 2013, everything changed. A breakthrough called word2vec came along and just flipped the whole problem on its head. Instead of just giving words a random ID number, word2vec found a way to learn a numerical representation that actually captured the meaning and the relationships between words. And this right here, this is the wow moment for word2vec. It's the classic example. It turns out that with these new vectors, you can actually do math with words. If you take the vector for king, subtract the vector for man, and then add the vector for woman, the resulting vector is incredibly close to the vector for queen. This was mind-blowing. It proved these numbers weren't just random. They actually held real-world semantic meaning. And it's not just about royalty, you know? You can see the same logic with countries and their capitals. Word2vec learns that the relationship, the vector that connects France to Paris, is almost identical to the vector that connects the USA to Washington, D.C. It's learning these real-world analogies, all on its own, just from text. So how on earth does it do this? Well, the core idea is surprisingly beautiful and simple. It's summed up by this phrase: you shall know a word by the company it keeps. Word2vec doesn't have a dictionary. It just reads billions and billions of sentences and learns that words that show up in similar contexts, surrounded by similar neighbors, should have similar vector representations. The actual training process is super clever. It's what we call a proxy task. You basically take a huge amount of text, you hide one word in a sentence, and you ask a simple neural network to guess what that hidden word is. It's going to be wrong, a lot. But every time it's wrong, it adjusts its internal numbers and tries again, millions of times. Now here's the secret sauce. We don't actually care if it guesses the word correctly. The real prize, the thing we're trying to get, are those internal numbers the network learned along the way. Those numbers become the word's powerful, meaning-filled vector. That's the embedding. And what you get at the end of all this is a total transformation. We go from those giant, sparse, mostly useless one-hot vectors to what we call dense vectors. They're way shorter, maybe just a few hundred numbers long, and every single one of those numbers is packed with information about the word's meaning and context. This is the heart of a word embedding.
So this is huge, right? We've got meaning packed into our numbers. But for the AI we use today, for the really powerful large language models, there's still one critical piece missing from the puzzle. We need to understand word order. See, word2vec was revolutionary, but it has a blind spot. It knows that man, bites, and dog are related, but it doesn't really care about the difference between man bites dog and dog bites man. For modern models like transformers, that's a gigantic problem. They need to know the exact position of every single word in a sentence to understand the true meaning. And the solution to this is, well, it's beautifully simple. We just create a whole separate vector called a positional embedding. This vector has nothing to do with what the word means. Its only job is to describe where the word is in the sentence. Is it the first word, the second, the 10th? And then you just add it to the original word embedding. So let's walk through how this all comes together step by step. Okay, first step, you start with your token, in this case, teddy bear. Next, you grab its token embedding. That's the dense vector from word2vec. That's just packed with meaning. This tells the model what the token is all about. Then you grab the positional embedding. This is the vector that only cares about the word spot in the sentence. This tells the model where the token is located. And finally, you just add them together. And boom, you have one single, incredibly rich vector that tells the AI both what the word is and where it is in the sentence. This position-aware embedding is the fundamental building block for all modern LLMs. All right, so we've built our final vector. It knows the what and the where. And this little piece of data, this isn't just some side note. It is the absolute bedrock of today's large language models. Seriously, think about it. Before a model like GPT-4 can do any of its amazing attention stuff, before it can process anything or generate any text, the very first thing it gets is this matrix of position-aware embeddings. This is the input. It's the raw material. Without it, the rest of that complex model has absolutely nothing to work with. So let's just pull back for a second. Why does all this matter? Well, for one, it's the magic trick that turns language, something fuzzy and human, into concrete math. It captures all those subtle relationships we understand intuitively. And most importantly, these embeddings are the high-quality fuel that allows these massive, complex AI models to even start their engines. And that leaves us with a pretty mind-bending question for the future, doesn't it? We figured out how to turn the abstract concept of a word into a meaningful list of numbers. So what else can we do that with? What happens when we turn the pixels in an image into vectors, or the notes in a song? What other parts of our reality can we translate into this language of numbers? And what new things will AI learn to understand next?